Hello everybody. Welcome to this sixth episode of Tensors. As we are continuing with this part on Tensor, we are now on the sixth episode of Tensor. Now, the response is quite good. I got a good many students who have been writing and asking me to do more videos on Tensor and especially contravariant and covariant vectors. So we are proceeding with that part. Now with this part of Tensor part 6, what we need to know a little bit, although most people would be knowing, but still it is important that we do a kind of a revision of what we call vector and vector spaces. So what we do over is that this is a nice little diagram that I have made during my leisure time. So what we do is that we will have to look onto something which we call vector. The usual definition of vector as it stands, but a little bit recent one about the vector that we know. It is not always the arrow part that we denote, and the vector spaces. So what do we actually mean by vector and vector spaces, and how do vectors behave under the transformation and change of coordinate system? So that is what we are going to we are going to target in this video. We need to go forward right now, and we have to see that if the video is getting quite long, then what we need to do is that we need to get a pause on this video and we will again make a next part of that video. So currently we will start with what is a vector, which is the sixth part of our tensor program. So this is tensor part 6, and we are carrying on with vector and vector spaces. So just to start with that, as we know that what is actually a vector, we will go by the basic definition of vector, which is quite common. And as we know that vector are generally denoted by arrows. So we will go by that. So this is an arrow, right? And it denotes a kind of a vector. Okay. Now the arrow of the vector denotes the direction in which the vector is happening. Is it in this direction? If I make it in upwards direction, that means the vector is pointing towards up. And the size of the arrow depends on what is the magnitude. So if I tell that this is around a vector which is 10 meters size, right? So it shows the direction in which it is going. Now it helps to visualize if I make something like this big, and if I make it look as 20 m, that means it is quite big. It is twice than that of 10. So that is how vectors helps us to know. So bigger the size, the bigger the magnitude. The direction can be this way, it can be this way, it can point towards this. So all these are signs of vector, which we denote by this one, and we can denote by this, which has got a hat on the top. Now once we talk of the labeling of vectors, we generally denote by V, but it is not necessarily like that. We can even denote it as A. Say for example, I write this one as 10 meters, so I can point this arrow towards this, or I can say it is C, which is pointing towards this one, and I can say this is 5 meter, so it is a little bit shorter than this. So the same letter of vector which we are denoting A and C, it necessarily means it is not a convention that you A and C, or you can use V, whatever the way you want. It is not strict that you have to use V or A and C. Now say for example, I would like to say that if we are not denoting it by an arrow or by a hat, so we can see something which is called a vector, and I can write this part as the scalar part, right? So if I say for example in vector I write A equals to 15 meter towards this direction, that means I've got an arrow which is pointing toward this, and in the vector we can just mention A equals to 15 m. That means I mention the magnitude as 15 m, I'm not mentioning the direction. Similar way we can write that B equals to 10 miles. If I write is B equals to 10 miles and I make the arrow pointing towards this, in the scalar part what I can do is that I can just mention 10 miles without mentioning any direction, right? Again what we can do is that we can use C, for example 20 newtons, which is a force which is being applied on this vector, and it is again pointing. And in the scalar part what we can also do is that we can just write 20n. That means it has got no direction. It is just the scalar part. the magnitude, that is up to 20 newtons. Now we will just look into some basic operations because this is important. So let us look into the multiplication part. So how do we multiply vectors? So I will just put it as multiply. Right, so how do we move? So multiplying a positive vector, multiplying a positive scalar by a vector keeps the vector in the same direction, but it increases the magnitude. So let us see how it happens. When we multiply a positive scalar by a vector, the vector in the same direction increases the magnitude. So for example, if I take the same example, we take A, for example, a vector. So I have to point it as an arrow. It is moving towards 10m, which is in this direction, and I have to multiply this particular vector by 2. So 2 times A, which is a vector, gives us an arrow value which is 20m. So I can make it this and then this, which is double the size. So this is the direction. So I can put it as A, which is pointing towards this, and this is 20m. Similarly, a very simple part, if we can multiply this by 0.5, that is, it will shrink down to 5 meter, which will be something like this. So I'm just multiplying this. A negative multiplication is also possible. So for example, if we use minus 2 times A, which is a vector, it would give us minus 20 meter. That means I have to push this arrow towards this direction, which is the opposite. So this is the negative part and these are the positive parts. So we can do the multiplication as positive and negative. So this actually is what we called vector multiplication. Now we can also look into some simple examples of vector additions. So let us see that how we can add a vector. For this I will use a different pen color, which will make things easier for you. So in order to add these vectors, we have a method which is called tip to tail. So I will write is tip to tail, right? And here is a vector. For example, I will just draw this one. Right, this has got a nice arrow. I will just color it, right? So this part is the tip. So I will mention this as tip. And this part is the tail part, which is the tail, right? Okay. So what we are going to do is that I have to draw another vector so that you can understand. So this part, for example, we have to draw another vector which is in this direction. This is nice. This is a nice vector. So again, this is the tip and this is the tail. So we have to add the tip to tail method. So this part will be added by this. So if we draw it in this way, so I draw this vector in this way, right, which is this part. I have to take the tail part, right? So I have to add this part here. So I add this one, and what I get is this part, right? So this is the resultant vector, or we can use Pythagorean theorem to find it out. So for example, this is 4 and this part is how much? This would be 3, right? So we can put it as 4 and then we can use it as 3, and this is, say for example, I put it as C. Then what we can do is that we can use C squared equals to 4 squared plus 3 squared, which gives us 16 plus 9, 25. So therefore C becomes 5. So I take a square root of this and this. Now this is one thing in which we can do the addition of vector, this and this, but remember when we are finding out this particular vector, it would be in this direction, right? So any vector which is pointing towards this, or if you're taking a vector which is pointing towards this way, we have to take the tip of this vector with the tail of this vector. So even if we take this one, that means the tip of the vector will be adding with the tail of this vector. So again, this is the tip and this is the tail. So all we need to do is that add the tip and the tail part. We'll just quickly look across few other examples so that the concept become clear. So what we will do is that we are going to do is that we are just going to take few more examples. So for example, I take another part. Now there are certain correct notions which are used in terms of using the tip to tail methods, and certain things which are quite incorrect. So just be aware that correct parts, say for example, if if I'm adding a vector, the tip to tail method in this way, see, I am using this one and I'm using this one, right? So this is the I'm using this and I'm using this, right? So what you need to note that if I am joining these two parts, right? If I am joining these two parts, so the vector direction, if I put it as this way, this is wrong. So I put it as wrong. This is not the part, right? So if I'm adding it in this way, it should be in this way. If I'm putting it up, it should be in this way. Then I will put a resultant vector or the hypotenuse, which will be in the direction of this. So this is right. Right, so this is wrong. Just mind it that whatever we are doing, so we can use this method. Say for example, this, I am adding this tip to the tail. So this is fine. And what I can also do is that if I want to add this tip to the tail, then this is also fine. But this is wrong. Right, this is wrong. So for example, if I get a vector, say for example, which is this one, I write it as 3 and I want to add it with a vector of length, say this one, which is 8. So what we will do is that we add the tip to this tail. So it would look at this length plus it will take this long. So what I will get is here is 3 plus 8 equals to 11. This is the way, tip to the tail, tip to the tail. Also what I can do, I can show you another example. For example, okay, so let us take a vector which is of length 6 and it is pointing towards this, right? And what we have got another vector which is towards this, right? So this is 2, right? But remember that it is in the opposite direction. So what I am going to do is that when we are going to add this one, so I'm going to add the tip to the tail. So this tip will be taking towards this tail. So it seems that it would be pushing. So here it would be 6 minus 2 equals to 4, right? So this is how we are going to do it. So if it is in the opposite direction, we get a negative part, and when it is in the same direction, we get a positive part. So this is how we do. Now we have to remember another property of vector, which is called a commutative property. So I will just put it across in words so that it is easy for you to remember. So we call it as COMMU, commutative property. It is called the commutative property of vector, right? So what is actually a commutative property? So it's quite simple. The order in which we add in regular numbers, it is the same thing. It doesn't matter. So the order finally doesn't matter in the way that we are adding. So for example, if I can show you like this. So regular numbers means, say for example, if I take 5 and 3, so 5 plus 3 gives us 8. On the other hand, 3 plus 5 also gives us 8, right? So this is actually what is called the commutative property. Whatever the order in which we are adding, it doesn't matter. It doesn't matter. So this same property is applicable in vector. So let us see how it happens. Say for example, we have got a vector in this direction. Okay, this is 12. I'm not writing whether it is meter or Newton. So let us assume for that this is 12. Plus we are adding another vector which is pointing in this direction, little bit longer, and I call it as 20. Right. So obviously it would result into 10 plus 12 plus 20 equals to 32. So it would be what we have shown earlier. This part is added to this part, and this would be 12 plus 20 equals to 32. Right. Now say for example, we take it a different direction. So I take another example. So if we take something like this, so we take a vector which is pointing towards this. This is 10. I'm not mentioning the unit, and we have got a vector which is pointing towards this way, and this is 20, right? So what is going to happen is that we are going to take the tip. So I will take this part as the 10, and I'm going to take the lower part which is going to be 20, right? So this is 10, this is 20, and we get a vector which will be this part, right? So it will be joined. So again we will be using the Pythagorean theorem. So finally it gives a result to something like, okay, so it would be 10 squared plus 20 squared equals to, let us mention it as C equal to C squared, this way 20 squared, so it will come to how much, 100 plus 20, 40, yep, this will be 400 equals to C square. So this would eventually, C would be equal to 500, sorry, root over 500. So whatever be the result. Now why I'm showing you this part is that now if this is done, okay, now if this is done, you will see that I will draw another analogy, which is something like this. The vector is pointing towards this direction, which is 5, and I'm taking the vector, another vector with addition, which is going towards this direction. Both of them are same, right? So what again we'll do, we do this 5 and we take this 5 and we get a vector like this, right? So this would be 5, this would be 5. So if I take this as C, it would be something around 7.07. So the basic idea of showing this is why I will tell you that whatever be the direction of these vectors, can you see this one? Now this is this is this and this, or maybe in this direction. The result of the vector is always the same. That is a vector. The vector remains to be the same. So I can point it in red. So this part and this part, it remains the same. So what I'm trying to tell you is that, let me summarize what I'm trying to tell you. So if I get a vector, okay, yeah, so this is fine. Yeah, so if I get a vector, say for example, this is this direction, plus I am adding a vector which is in this direction, right? Case 1, right? So whatever it happens, it will be eventually what it would result is that if I will get this part, or it might be if I'm getting a vector which is in this direction, okay, and I'm getting a vector in maybe in this direction, so I'm adding sorry, it would be like this direction, that is, and I'm adding in this direction. So the yeah, so again the result would be this. So this part which I'm talking, this part is always the same. This part remains to be the same, right? So that is what we need to know, that whatever it happens, the vector arrow or the direction of the vector remains the same. So till now everything is fine. I think we are proceeding nice and fine. So I don't think that we need to revise on anything. We have just shown you that what is a vector, and this is basically how we can use a vector and a scalar, the distinction. We have shown you how we can multiply the vector, and from tip to tail how we can do the addition, and by using geometry and Pythagorean theorem we can get result of the vector. But do remember that vector is a commutative property. It has a commutative property, and it shows that the direction of the vector, whatever the way it is proceeding towards, it remains more or less the same. It remains more or less the same. Right. So let me just revise. So how we can define the vector. So there is a nice little definition of vector. So let us quickly read out. A vector space is a collection of objects called vector, which may be added, multiplied, scaled by numbers called scalar. Right. So this is what is called a vector space. But we are not dealing with the vectors. We are coming to the vector space part. Right. So yes, so now what we will do is that our next part of the video would be dealing primarily with vector space. So I will just show the heading right now. So we will be dealing with this part. Okay, so we would be now dealing with the vector space part. So I just thought to show you this part, which is a vector space. So we are done with vector addition, multiplication, adding and showing through tip to vector part, right? So now what we will do is that we will deal with vector space. Now what is a vector space? Let us see our basic definition of what is a vector space. A vector space is a collection of objects called vectors, which may be added, multiplied, scaled by numbers called scalar. Now what I would like to draw an attention to the viewers is that in general vectors are always denoted by arrows, right? Now this is a wrong notion. This is a wrong notion, because in general there are a lot of vectors which will be coming up in Einstein's field equation and further, which cannot be defined by an arrow, right? Which cannot be defined by an arrow. So in general in our school days, or the teachers would teach us that vector is represented by an arrow. Even I started the video showing you that vector is an arrow, but vector showing by an arrow is erroneous. The reason is that all vectors cannot be denoted by arrows. Only those vectors which are denoted by arrows are in Euclidean vectors, but there are a lot of non-Euclidean vectors, areas, groups, which I would like to show you. Right. Now, when we are telling with vector space, we have shown that a vector space is a collection of objects, right, called vectors, which may be added, multiplied. So these are it contains certain other operations. Now, considering this fact, let us see that if we want to generalize vector to an n-dimensional space, see what I have done over here is that I have shown you, say, vector v. Okay, it has got v1, v2, v3, v4, v5, v6, so on up till v10. Similarly, we have got a vector w, which has got w1, w2, w3, w4, w5 up till w10. This has also got an additional property. So vector v added with vector w gives v1 plus w1, v2 plus w2, and so on, right? And it also has got a kind of a multiplicative property. So this is C is the scalar part, which has been added by C v1, C v2, C v3, C v4, continue till C v10, right? So what I am trying to show is that I'm just trying to give a kind of an n-dimensional space. So n-dimensional space is a space where forces are described by n coordinates. Now what I'm trying to mean by this particular definition is that in general, when we show the coordinates, it can be this way. There's the x, y, it can be the z direction, right? There's the x, the y, and the z direction. If we go with Einstein's field equation, we will also see that we are taking time and so on. But this are 1, 2, 3, 4. How many? Till 10, anything. So what I'm trying to show you is that if you want to generalize this part to to 10, and from 10, then I take on to n-dimensional space. So that is what is called a n-dimensional space, which is where the forces of physics are described by n coordinates. Now, so we have understood what is a vector space. So vector space is what? It's a collection of objects, definitely called vectors. So we will wait till that, which may be added, multiplied. We will come to that part later. So when we talk of objects which are called vectors, we also need to see that what are the properties of a vector space. So let us quickly see a basic overview. I have purchased time by writing these on a sheet of paper so that it becomes easier for people to understand, right? What are the properties of vector space? So mind it that a vector space, because it is a collection of objects which is vector, should have an addition, right? So if it's a vector v with a vector w, so I can add v plus w. So this is property number 1, that a vector space should have an addition. Commutativity is v plus w. This is simple, like I mean to say, if you take this, it is simple, like 2 plus 5 and equals to 5 plus 2. So commutativity doesn't depend on which order it has been added. So this is that. We have another thing which is called a zero vector, which has got no length. It also has a zero vector. Identity element, so a vector which has been added by 0 gives back to this vector. I think this is also the same, like if you add 5 plus 0, it gives you back the value. So this part, if I call it as vector v, the normal elements also carries this identity element. So note what I am trying to mention. What is my basic objective? I am trying to draw an analogy with the real numbers along with the vector part, right? So this has got an identity element. So you see that addition is common in normal numbers. Here it is also there. Commutability is a part of the normal number. Real numbers, it is there. 0 is there. 0 vector is there. Identity element, any vector added by 0 gives you back to this vector. Inverses are also there. See, 5 plus a negative vector, I think it won't be this. It should be pointing towards this direction, right? So this is wrong. It should be in this direction. Anyway, so v plus minus v equals to minus v plus v, which gives 0. Obviously, if I take the real numbers 2 minus 2, it gives 0, right? Associativity. This is called associativity. Associativity is what? Associativity is a vector, say for example v, right, and which has got a property plus w plus z, which are two vectors, also give you v plus w plus z. So I can take a similar kind of an example. I can take 2 plus say 3 plus 4, right, is also equal to 3 plus 4, that is the w plus z part, sorry, v plus w. So it would be 2 equals plus 3 plus 4 therefore would be equals to v plus w, so 2 plus 3 within bracket plus 4, right? So this will give eventually 9. This is also going to give 9. So see, all the real numbers are the properties which are available in vector space, and it is also in the real field, it is also available in vector space, isn't it? Right. So we can summarize this one. Vector spaces are commutative groups. In one way, vector spaces are commutative groups, right? But we have to find out that vectors are even more than this. Vectors are even more than this. So we will start with this example. What do I mean? So this part I think is quite clear from the properties. I have shown it with real numbers, which actually matches with the vector. So what do we mean by more than this? Okay, so here we are. Let us see an example. What we call is a scaling of a vector. So let me write it down. It is called scaling of a vector. Scaling vector. So I will just put it like this, right? It is called the scaling vector, right? So scaling vector, say for example, if I get a vector, I will denote it by v, right? So v, and I will just define it as, say for example, v1, then v2, then v3, and dot 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 dot, it will go up to vn, right? So this part definitely I can write that if a scalar c, and I'm using this one, this is called a notion, this is a symbol of set theory. It includes r. I have to write it in bold because this would mean all the real numbers, right? So I can tell this way. I can also tell that c, if it is a scalar, multiplied by the vector v, eventually would give me c v1, right? And then it will give one cv2 and cv3 and dot dot dot, it will carry on till cvn. So it has also got this property, which is multiplied by the scalar. So you can see a vector when multiplying each coordinate is by a real number. This is the real number r. So this gives us vector spaces additional properties than ordinary groups. This is what I was calling you, that it gives us an additional property other than the ordinary groups. So what are those properties? So let us look on those properties of scalar. I have listed it down just to save time. So here it is. Yes. So here it is. So see, the properties of scalar is called a distributive property. That is c again. Okay, I will just again I will show you with real numbers. So c multiplied by v plus w equals to cv plus cw. This part is a distributive property, right? Then we have got c plus d multiplied by v vector equals to cv plus dv, obviously. So can I draw a kind of a real number? Say for example, c is 2 plus 3 multiplied by 5, okay? And I can write this as, so there cv, right? cv, that means 2 multiplied by 5, plus I can also write dv, that is 3 multiplied by 5. So 7, 10 plus 5, 15. So 10 plus 5 equals to 15. So what I am trying to show is that these are real numbers. So I will put it as big R. This is a big R, which is a general notion of a real number, right? So this is what we show. It's a real number. Also, it has got an associative property. This is an associative property. C multiplied by d dot v dot equals to c dv. So let us see, for example, if I take another example, I will take the same one. So I will take 2 multiplied by 5 and 3. I can tell it this one would be equal to cd, that is 2 and 5. Yeah, cd, yeah, 2 and 5. 2, 5, and I can put outside the v part, that is 3. So this is again a real number. Okay, so it has got a distributive property, which we have seen. We have also seen it has got an associative property, and it has a property which is unchanged, that is 1 multiplied by any vector gives you back the vector. So we can see it even in real numbers. 1 multiplied by 5 or any real number gives you back that number, until and unless you are obviously multiplying it by 0. So you see that what we have seen over here is that the properties of a scalar, which gives an additional part in terms of scale. We have seen what is a scaling vector. So properties of scalar, it has got a distributive property, it has got an associative property, and it has got a property where multiplied by 1, it will lead you to the same results. Okay. So what is the final definition? Where do we go? Where do we find anything which is called a vector space definition? Here it is. This is a kind of an, I won't say abstract, but still it, get rid of those arrow parts. So a vector space definition, let us read it what it says. It is a commutative group, obviously. A field of scalars, if I take it as capital F, it is a field of scalars which contains capital F. I am mentioning it. V, small v, which is a vector, includes, this is set theory sign, includes v as a vector, and obviously small f includes f as a scalar. So what I can tell from this as that f, that is the part of all the fields of scalar multiplied by a vector, gives back you to the vector. Alright. Distributive property is quite simple. F v1 v2 gives us f v1 f v2. I think I don't need to show it by real numbers. This is quite obvious. So if I say for example 7 within bracket 2 plus 3, okay, it would give us to how much? 7 into 2 plus 7 into 3. So this is the distributive property, some certain cases. So this is another example, f1 plus f2 multiplied by v. Associative property. So we have seen this one. I think this is quite clear. f1 multiplied by f2 fv gives you this one. And vectors are unchanged when multiplied by 1. Vectors are unchanged when multiplied by 1. So this is more or less a kind of a very, I would say an abstract and more or less a good definition of what a vector space is all about. Right. It has got a commutative property. It has got a field of scalars of vector. V includes V, this one. It has got a distributive property. It has got an associative property and a unit property where vectors are unchanged when multiplied by 1. The question is that can we further generalize all this definition into a kind of a matrix, because we are dealing with something which is linear algebra. Here it is. I've written again this one just to save time. So to generalize the definition of a vector, we can use a matrix. This is a 2 by 3 matrix. These are the 2 by 3. It has a 0 vector, obviously. 0, 0, 0, all this, it has got a 0 vector. It has got inverses, negative signs, right? And it has got a scalar multiplication. So we can do the scalar multiplication, C being the scalar, we are multiplying it by a 2 by 3 vector and we are getting the result. So here is the final one. 2 by 3 real matrices form a vector space. So you might be thinking that why I'm doing all those things. The reason that I'm doing all those things is to tell you that the vector space is actually collection and it can be generalized into various parts. So we have seen the properties of vector, which is this one. We have seen the properties of a scalar, which is this one. We have also seen the vector space definition, which can be called this one. It is a commutative group, it's a field of scalars, etc. And we have also seen this one, which is the properties of scalar. This is the properties of scalar, distributive, associative, and unchanged. The final property, which now I'm going to show you, which is also will generalize the notion of vector. It is not that we really want to get rid of those arrows, is that the use of an polynomial. I will just not take much time, I'll just quickly follow through that. So all polynomial of 5 or less, for example, forms a vector space. So can we write it down? Say for example, okay, so I will just put this paper up. Okay, so let us see for an example. So if I write down a kind of a polynomial equation, so we put it as a 5x5, right, plus a 4x4, so and plus a 3x3, okay, plus a 2x2, and I use a1x1, a1x, so plus a1x, and I use a0. So this entire equation of polynomial of degree 5, I can use this one. This would be, I can tell that if I generalize it as ai, this would be a part. Again, I'm using this equation, which means it resembles a part of the real number. It resembles a part of real number, right? So all polynomials of 5 or less, this is also part of the vector space, which is a real number. Now adding two polynomials, let us give you an example. For example, I've got an equation. Say for example, I have got 2x5 plus 3x to the power 3 minus 7x plus 11, right? And I'm going to add this one. I'm going to add this one with 3x5 plus 6x4 plus 5x, right? So what do we get from here? We will get how much? This would be 5x5, right? Minus 6x4, this would be x4, right? Plus this would be, as it is, 3x cube, and this would be 7 minus 5, how much? 2x plus 11. Now what is important is that you see that this polynomial equation gives you so it gives you an equation which is degree 5 or less. You see 5, 4, 3, 0, 1, 1. So this will give you a polynomial of degree 5 or less, right? So again, say for example, if we quickly do another equation, and in this way we are going to add this part. Say for example, I got another equation. Say for example, if I write f equals to 3x to the power 5 plus 5x cube minus 2x plus 9, right? And I'm going to add with another one, which is g equals to minus 3x5. I'm doing this because I want to wrap this up. It is going a little bit longer. 8x squared plus 4x minus 2, right? So what would be the result? So let us see it. F plus g, how much it would be? It would be, this one would cancel out. This would be 5x cube, right? Plus this one would be 8x to the power 2, plus this would be 4 minus 2, 2x, 9 minus 2, minus 7. So again it gives us a polynomial of degree 3. You see this part is polynomial of degree 5, and this one is the polynomial of degree 3. So this is degree 3. This is degree 3. So what I am trying to point out over here is that if given a polynomial equation, if you are adding it in the same group, it is definitely going to give you a polynomial which has got the same or the lesser powers. This one was degree 5. This has given 5, 4, 3. This was 5, 3, 5, 3. 5, 2, it has given 3, 2. So it would be either less, but it cannot be more. So I will put it in red. It cannot be more. When I say that it cannot be more degrees, I mean to say it cannot go from 5 to higher. That means it cannot reach up to 6 or 7 or 8. Now I have to pause here, right? This is basically vector and vector space. I will be coming up with what is called how vectors behave in the change of coordinates in the next video, because you can see that it is already 37 minutes and it has just taken me to make you understand about what is vector space, etc. So just a kind of a quick revision before we wrap up, and I'm going to just tell you those definitions. So vector space, we have seen what it is. A vector space is a collection of objects called vectors which have got addition, multiplications and all those properties. I think we have seen enough amount of multiplication properties. This was the first through why I have shown that you can generalize things into different parts, like you can call it as a n-dimensional space, etc. Properties of vector space, it has got this, I would say 6 properties. It has got an addition, it has got commutativity, it has got zero vector, it has identity element, it has inverses, and it is an associativity, which can be finally termed as vector space or commutative groups. Further, this was another definition of vector which has shown the commutativity, associative and the distributive properties. We have also seen what are the properties of scalar. We have seen that it has got distributive property, associative property, unchanged property, and it can be further generalized in the form of a matrix which has got the inverses, the zero and the scalar multiplication. So 2 by 3 real matrices also forms a vector space. So that brings us to the end of the video. What is vector and vector space? The basic idea of doing is not to show the traditional way of using arrows, although I have used arrows over here, but it is something more than that. So just watch out for my next video, in which I would be speaking mostly about how vectors change with the change of coordinates, and obviously the most important part, that what is a contravariant and what is a covariant vectors, because unless we understand what is a covariant and a contravariant vector, we are unable to understand the Einstein's field equations. So that brings us to the end of the video. I hope you have liked it. If you have any comments, you can put it up in the comment section. If you want me to make more videos on vectors or areas into linear algebra, let me know. Please like it, subscribe to my channel. Thank you very much for watching. Click on the bell icon to get the notification. Thank you for watching. Stay safe, stay happy, and watch out for the next video on co and contravariant vectors. Thank you very much. Have a nice day.